Hi friends, welcome back to Quant Street and to a new edition of the tutorial series on various quantitative fundamentals. Today I'll be talking about the AR1 process. AR stands for autoregressive, and we'll see why they use the term regressive and auto and 1. So basically we define an AR process as follows. So yt equals some constant mu plus phi, another constant, times yt minus 1 minus mu plus epsilon t. So let's try to break it down, the various components. So as I said, mu and phi are constants. Yt minus 1 is the one time period previous value of yt process, and that's the reason why we use this term 1 over here. So because we are the yt is dependent on yt minus 1, and that's why there is some amount of correlation that we are trying to model here. And finally the component, the last component is epsilon t, or we can call it an error term. It's not the right way of writing error, so let's write it again, error. And it's modeled as weak white noise. So epsilon t is weak white noise with a mean of 0 and a variance of sigma epsilon square, and it represents new information. So for example, if you're looking at a stock price, the random factor that makes the stock price go up and down on a daily basis is all the news in the macro and micro economic level around that stock, and that news may not be dependent on the previous day's news. So this epsilon t represents the movement due to that move or that news, and that's why it represents the new information, and that's an important part of this AR1 process. So now that we've broken down, let's take a look at some of the properties of AR1 process. Okay, so let's say we have this AR1 process, y1, y2, and so on up to yt. If this process is weakly stationary, so weakly stationary process we've already defined in our previous episode of this tutorial series. You can take a look at that. So if y1, this y process is a weakly stationary process, then let's say the variance of this of say t minus mu equals the variance for yt minus 1 minus mu, and that's understood because it's a weakly stationary, so variance is constant. So which means sigma y square equals phi square sigma y square plus sigma epsilon square, which implies that the value of phi square is less than 1 or phi absolute is less than 1. So that's an important aspect of a weakly stationary process, that the value of this weight on which the value of a new process depends, that weight is less than 1. Now the equation for yt, which was mu plus phi times yt minus 1 minus mu plus epsilon t, so we can rearrange it as yt equals mu times 1 minus phi plus phi times yt minus 1 plus epsilon t. So this equation is equivalent to a linear regression. So this equation represents a kind of linear regression equation. If you want to show a general linear regression equation, it looks something like this: beta 0 beta 1 times xt plus epsilon t. And so we can correspond each of these terms. So beta 0 is a constant, and mu and 1 minus phi product is also a constant. xt can be equivalent to yt minus 1, where beta 1 and phi are equivalent, and epsilon t's are as well. So the term autoregression refers to the regression of the process to its own past values. So in a way, yt is regressing to its own past value, yt minus 1, and that's why we use the term autoregression. And 1 signifies that we are just looking at one time period back, and that's why this yt minus 1 and ar1. So let's try to simplify it further. So if phi absolute is less than 1, we can basically rearrange this to yt equals mu 1 minus phi plus phi yt minus 1 plus epsilon t, and basically I can also use yt minus 1's representation, something like this, plus phi yt minus 2 plus epsilon t minus 1. Just expanding that definition of yt, 1 minus phi times mu plus phi times 1 minus phi times mu plus phi yt minus 2 plus epsilon t minus 1 plus epsilon t, which basically equals mu minus mu phi plus phi times mu minus mu phi plus phi yt minus 2 plus epsilon t minus 1 plus epsilon t, which equals mu minus mu phi plus mu phi. So these two can cancel out, and then minus phi square mu plus phi square y t minus 2 plus phi epsilon t minus 1 plus epsilon t. And we can continue this further, expanding for yt minus 2 with yt minus 3, and when we do that expansion, this term gets cancelled out and we have some additional terms with something like phi epsilon t minus 2, and so this can be generalized to a simplified form. So this recursive action can be generalized to form this kind of an equation, that yt equals mu plus n equals 0 to infinity phi to the power of n epsilon t minus n. This is also called as infinite moving average representation, and we can say that yt is a weighted average of past noise. And so it seems that we are approaching some kind of a parsimonious model with this. As we can see that it mostly depends on this constant phi mu and the distribution for epsilon. But the condition here is that phi is less than 1. The absolute value of phi is less than 1. So now let's take a look at some of the properties of the AR1 process. So the expectation of yt equals mu for all t. Variance of yt equals gamma 0, which equals sigma square y, and let's see how we can derive this. So here we'll be using the formula for variance, which is variance of omega t y, where omega and t are matrix representations and t is the transpose is individually it can be represented like this: omega I times yi, which is I1 to n omega I square times variance of yi, and if we know the variance of yi, we can easily find or represent the overall variance in terms of variance of yi. And so if we look at our variance equation here, we know that yt equals mu plus summations n equals 0 up to infinity phi to the power of n epsilon t minus n. So if we want to have the variance of yt, which equals variance of mu plus summation n 0 to infinity phi to the power n epsilon t minus n, and variance of mu will be 0, and this based on the formula before can be simplified as so phi to the power of 2n times variance of epsilon t minus n, which we basically already know, and this is sigma epsilon square, and this can be represented because phi is less than 1, so this can be an infinite series of fractions, and if we add all of that, we get 1 by 1 minus r, so doing a summation over infinity, and so this becomes basically sigma square epsilon by 1 minus phi square. So that's the variance of yt. And now let's take a look at the covariance of yt comma yt plus h, which equals gamma of h, which equals phi h modulus sigma e squared over 1 minus phi square. So we have an additional term here for variance of 2 time series spread out by h. And correlation of again these two equals covariance divided by variance, which basically simply equals phi to the power of h for all t and all h. So basically the ACF or auto correlation function depends only on this parameter phi, which represents enormous amount of parsimonious model, but this has its own limitations, as I will show next. So if we take different values of phi at 0.95, at 0.75, at 0.2, or maybe a negative value less than 0 and greater than -1, then these can be basically plotted as follows. If you plot the autocorrelation for these four, it will be something like this. So this will be the case for 0.95. For 0.75, this will be the case, so it will be a little steeper. For 0.2, it will sharply decline and reach a correlation of 0. So just a reminder, we have on y-axis we have autocorrelation function, and if it's a negative value, say 0.9 negative, then it will jump around this with declining amplitude and come to rest to 0. So it's a very few set of functions that this parsimonious model is covering, And to remedy with this, we'll talk about this next. We use more AR parameters, or we switch to another class of models which are called moving average MA models, or a combination of AR and MA called AR MA or ARMA models. So that concludes today's episode. I hope you liked it, and if you did, please consider subscribing. Thank you again for your time. Quant Street signing out.